Hello, my name is Abir Islam, and I will be presenting an analysis of Tor's privacy. Let's get started. So, first, let's talk about the background of Tor. So, Tor is an acronym and it stands for the Onion Routing Project, TOR. Onion routing is a protocol that was developed by the United States Naval Research Laboratory, and this was done in the mid 1990s. Some notable names that helped engineer this include mathematician Paul Syverson and computer scientists Michael Reed and David Goldschlag. It was built to protect United States military communications, and it launched on September 20th, 2002, internally. But it was then released to the public a year later. So you're probably thinking, why was it released to the public? An application or a protocol that was built to protect a country's military communications should not be released to the public, right? Well, it turns out that if only U.S. military or U.S. intelligence organizations use Tor, then everybody would know that it's the U.S. government or military or intelligence organizations. For example, if you're monitoring internet network traffic and you see someone using Tor, then you already know it's only the US military because only they have access to Tor. So Tor's anonymity system only works for the US military and US intelligence, and also everybody else in general, if there's a big, large pool of users creating traffic so that everyone blends in together. And it's free and open source today, as in 2004, the Naval Research Laboratory released the code for it, and then in 2006, the Tor project was founded to maintain it. So how does it work? So Tor is an anonymizing protocol that uses onion routing to hide the source of TCP traffic. So what exactly is onion routing? Well, onion routing is when your internet traffic is routed through multiple relays, and relays are basically just servers run by volunteers that forward internet traffic. And client traffic typically goes through 3 relays, and the relays are known as the entry or the guard relay. It has 2 interchangeable names, the middle relay and the exit relay. And the exit relay is the relay that finally connects to the destination, which is basically the content you're trying to access when you're using Tor. This could be a website like youtube.com or reddit.com. So the client performs Diffie-Hellman handshakes with each relay. And we talked about this handshake in class with the analogy where, let's say there are 2 people, Alice and Bob, and both Alice and Bob pick their own secret colors. And then they mix their secret colors with a publicly known color that they announce. And then they swap their mixture. So the public would know the publicly known color and they would know their mixture colors. And then once they get each other's mixtures, they would add back in their own secret colors, which would give them a shared secret color that no one else knows. And this basically is a shared secret key. So this handshake process establishes encryption keys that only each relay knows and shares with the client. And this is so each relay can only decrypt one layer when the request is made. Each path through the relays actually changes every 10 minutes. So every 10 minutes, new handshakes have to be done. And when a user visits a site from the exit relay, the traffic appears to come from that exit relay rather than the user's computer. So here's a diagram of how this all works. So we have a client, we have relays A, B, and C, and then we have a website such as CNN.com. And then, so first, the client wraps the request. So they would wrap a HTTP request for CNN.com in encrypted with keys CBA. So it's specifically in this order, CBA, because when it first sends the request to A can peel open that request. So they decrypt that request, which is so they decrypt that request. They see only the part that is encrypted with C and B, so they don't have any other information other than that. And then they know to forward it to relay B, so they do. And then B, once B gets it, it decrypts B's portion, and all that's left is C's portion, and then it sends over that portion to C, and then C decrypts that last portion, and then it finally reveals that HTTP request to CNN.com. So then they make that request, and they fetch it back, they get back the data, and then they re-encrypt it. So they re-encrypt the, let's say, the HTML file of CNN.com with its own key, and then it sends it to B. B wraps it and encrypts it with its own key. So now it's CB encrypted, and then it sends it to A. A again wraps it with its own shared key, and then it finally sends it back to the client. So one thing to note is that, when it gets to the client just decrypts it using A, B, and C in order, because A is, again, the outermost layer. And then you should know that this causes significant network overhead because it has to jump through 3 middlemen to get to the content and then back again. And then it has to be encrypted in each location too. So this means that internet performance will be much, much slower while using Tor. So the problem, does Tor achieve privacy? So Syverson says, because the public Tor network is comprised of thousands of relays in the network all over the world, it would be difficult for an adversary to watch all or even most of them. And this sums up Tor pretty well because there's so many relays in the world, and relays are being constantly added by new volunteers. So it's very difficult to determine who the client is and what they're trying to access. Onion routing protects identity from their activity. So no single relay knows both the client's IP address and their destination content. Because if you think about it, only the entry relay knows the client's IP address, and only the exit knows the destination. The exit does not know the client's IP address, and the entry relay does not know the request because it hasn't decrypted the entire message. And the middle relay does not know the IP or the request. It only knows the other 2 relays. Encryption prevents traffic analysis by the individual relay. So obviously, again, each relay can only decrypt what the other relay sent, and it can't decrypt the entire message. And reputation-wise, Tor does achieve privacy. If you look at its track record with Edward Snowden, he used Tor when leaking NSA documents, but then he chose to publicly reveal himself because he would be found out sooner or later, as he was an insider with access privileges to that information that he leaked. So advantages of using Tor. So by routing traffic through relays, Tor helps protect what a user views online, obviously. And local network admins, internet service providers, and governments cannot see what websites a user visits. So this means that users are basically protected from their schools or workplaces from spying on their internet traffic. By having 3 relays, no single relay will know both the client and destination. We talked about this. It's free and open source. This means that anybody can run relays or use the Tor network. And Tor combats censorship. So users in restrictive or authoritarian countries like North Korea or China can access blocked websites. And the only way these countries would be able to prevent this is by blocking every single Tor relay, which, if you think about it, is practically impossible because new ones come up all the time by volunteers. You or me could open up a Tor relay, and all it would take is one relay that isn't blocked for the individual or the client to gain access to whatever content they're trying to get towards. So limitations. There's the correlation attack. If an observer is able to see both ends, then anonymity is compromised. So to do this, the observer needs to monitor the client to the guard relay or the entry relay traffic, and this lets them know who you are or what your IP address is, and then they would need to monitor the exit relay to the destination traffic, and that would obviously let them see what content you're trying to access. But then, even though they have those two pieces of information, they still need to correlate the timing patterns of when you sent the request, the internet packet size of the request, and the internet traffic activity so that they can link your identity to the request you're making with high confidence. And the only people that are able to have the infrastructure set up to monitor large portions of the internet like this would be like a nation state or a government or some sort of internet service provider to be able to employ this. But internet service providers, if you think about it, are actually in a good position because they already have access to the client information. If, let's say, you're with Verizon, they already know your IP address because they assigned it to you. And so they know the guard, they know when you try to visit the guard or entry relay. And then if they also happen to be the internet service provider for the destination, they control the exit relay. So with this, they can do a correlation attack and see what you're up to. Adversaries can employ a tactic known as website fingerprinting. So how this works is that they first visit the website themselves, so they could visit yahoo.com, and they record the pattern of bits that they download from the homepage or the HTML page. And then if later on they see a Tor client exchange the same pattern over the relay path, even if the relay path is encrypted, they have some idea as to what website the client is visiting. And if the adversary monitors the traffic between the client and the entry relay, then the adversary therefore can link the client to what they're visiting. So Tor can't help anonymize a compromised device ridden with malware because that device can see everything and just log everything on the screen. So it would not help if you have viruses or malware on your computer. And then obviously internet speed is much slower. We talked about this, as you have to jump through multiple hoops. So Tor, conclusion, Tor is not 100% private, but it is very, very private. The only major attack that could really break Tor is the correlation attack. And again, this is only feasible for an organization that can monitor traffic between thousands of relays. Tor is actually much more private than VPNs. So if you think about it, Tor is kind of like jumping from one VPN to another VPN, but with added on encryption between these two like VPNs. But Tor is decentralized, whereas VPNs are run by a few companies, which means that no relay provider can know both you and your destination. But if you were to VPN hop using the same VPN provider, say you're using NordVPN, then that provider can know everything. But in contrast, using a VPN does give you significantly better internet speed at the cost of anonymity, of course. And Tor is one of the strongest privacy tools available. It provides anonymity that even governments would find very difficult to break. And then a real world example of how private Tor is, if you know about the Silk Road incident, the creator of the Silk Road was actually caught not because Tor was compromised, but because of server misconfiguration and other issues, not because Tor was compromised. And here are my sources. So I know it helps to have an actual practical demonstration of Tor instead of only hearing about it. So I have opened up my Mozilla Firefox browser on the left side and Tor browser on the right, and we can actually see Tor in action. So although I'm not going to look up what my IP is in my Mozilla browser, I can search for what my IP is in my Tor browser. So if I do what's my IP, again, the request is going to take a while because it's much slower, but we can open up whatismyipaddress.com, and then it says that IPv4 is 82.221.100.12, and my IP actually starts in the 90s, so I can already tell that this is not my internet. it says FlokiNet EHF. If we open this up a bit more, we can see that it's in Reykjavik, Iceland. So this, you already know that this is definitely not me because I am in the United States. So let's actually test my internet speed, and then we can compare it to Tor's internet speed. So if I do internet speed test, we can see that I'm getting around 300 megabits per second here. And then we can just go from here. Okay, we're getting roughly 50 up. And let's test it on Tor. So what's our internet speed? I wonder if DuckDuckGo actually has internet speed built in. It doesn't, but we can do Ookla's. Oh, we need to do a security check. Okay, let's test it out. And this is, again, taking a while. And you can see how big the difference actually is. So using my naked internet, it's roughly like 7 times faster than using Tor. Which obviously makes sense because it has to jump through 3 relays and then 3 relays back, all while encrypting in the middle of them. And then that's it.